Hello YouTube, my name is Neil and we're studying for the MCATs today. We're in the Organic Chemistry Review, Chapter 6, Aldehydes and Ketones 1, Electrophilicity and Oxidation Reduction. This chapter focuses on an important functional group for the MCAT, the carbonyl. Aldehydes and ketones, the two functional groups highlighted here, have a lot in common because they both contain a carbonyl, a double bond between a carbon and an oxygen. The only difference between the two is what is attached to the carbonyl carbon. The carbonyl group is one of the most common functional groups in organic chemistry for two reasons. First, the carbonyl is a component of many different functional groups. In addition to aldehydes and ketones, the carbonyl is found in carboxylic acids, esters, amides, and hydrides, and several other compounds. More importantly, the carbonyl has the unique ability to behave as either a nucleophile, as in condensation reactions, or an electrophile, as in nucleophilic addition reactions. In this chapter, we will investigate the overall properties of aldehydes and ketones, as well as their oxidation reduction reactions and electrophilic properties. In the following chapter, we will investigate their nucleophilic properties through enolate chemistry. A ketone has two alkyl groups bonded to the carbonyl, whereas an aldehyde has one alkyl group and one hydrogen. This means that the carbonyl in a ketone is never a terminal group, whereas it is always in an aldehyde. Like many organic compounds, aldehydes and ketones are often strong-smelling compounds. Volatile carbonyls are found in many species, including cinnamon, cinnamaldehyde, vanilla, vanillin, cumin, humaldehyde, dill, carvenone, and ginger, zingerone. Nomenclature. Aldehydes are named by placing the E at the end of the alkane named with the suffix Al. Common names for the first five aldehydes shown in figure 6.1 are formaldehyde, acetaldehyde, propionaldehyde, butyraldehyde, and valoraldehyde. When aldehydes are named as substituents, use the prefix oxo. So let's write down a couple things. Write down that aldehydes are terminal, ketones are not terminal. What's the opposite of terminal? Let's write not terminal. Aldehydes have the oxygen double bonded to a carbon, bonded to a hydrogen, whereas the ketone is a double bond to a carbon that's bonded to two other carbons. And then we have some common aldehydes. Let's write down a couple of these. The trivial methanal or formaldehyde. You got ethanal, propanal, one, two, three, There's too many. 1, 2, 3, 4, 5 hydrogen. Butanal. And finally, pentanal. Pentanal is also called valeraldehyde. Butanal is also called butylaldehyde. Propanal is called propionaldehyde. Ethanal is called acetaldehyde. If the aldehyde is attached to a ring, the suffix carbaldehyde is used instead. This is shown in figure 6.2. Oh yeah, I also wanted to write the oxo prefix. And the carbaldehyde suffix if attached to a ring. All right. Naming cyclic aldehydes. Cyclopentane carbaldehyde. We have a 5-carbon ring, cyclopentane, and then basically methanal, a formaldehyde, but it's a carbaldehyde. All right. Ketones are named by replacing the E with the suffix ONE. When naming ketones by their common names, the two alkyl groups are named alphabetically, followed by ketone. When ketones are named as substituents, we use either the prefix oxo or keto. All right. You know what? Let's also put al as a suffix. And then for ketones, so these are aldehydes over here. These are ketones over here. Own. Oxo or keto. Let's also put down ketone. Ketones, naming ketones, we have 2-propanone, which is also dimethyl ketone or acetone. We have 2-butanone, which is also ethyl methyl ketone. We have 3-oxobutanoic acid. So the acid part is carboxylic acid, but the ketone part here is the oxo. And then in cyclopentanone, we have a 5-carbon ring and a ketone on one of them. Let's write down just a couple of these, like acetone, since it's pretty common, also called propanone, 2-propanone, I guess. I mean, can there be any other? Because if it was on either the other carbons, it would be an aldehyde. It would be propanaldehyde or acetaldehyde. No, it'd be 1, 2, 3. It'd be propanal, propionaldehyde. All right. Propanone's also called acetone. And we'll leave the rest. Physical properties. The physical properties of aldehydes and ketones are governed by the presence of the carbonyl group. The dipole of the carbonyl is stronger than the dipole of an alcohol because the double bonded oxygen is more electron withdrawing than the single bond to oxygen in the hydroxyl group. In solution, the dipole moments associated with these polar carbonyl groups increase intermolecular attractions, causing an elevation in boiling point relative to their parent alkanes. However, even though aldehydes and ketones have dipoles more polar than those of alcohols, the elevation in boiling point is less than that in alcohols because no hydrogen bonding is present. In reactions, aldehydes and ketones both act as electrophiles, making good targets for nucleophiles. This is due to the electron withdrawing properties of the carbonyl oxygen, which leaves a partial positive charge on the carbon, as shown in figure 6.4. Generally, aldehydes are more reactive towards nucleophiles than ketones because they have less steric hindrance and fewer electron-donating alkyl groups. So let's write some of these down. So aldehydes and ketones don't have hydrogen bonding. So they don't have elevated boiling points like alcohols. But they make good electrophiles. This is for both aldehydes and ketones. That they make no hydrogen bonds. They make good electrophiles. And ketones have more steric hindrance. So aldehydes will be a little more reactive. Formation. Oh, and then we have the figure 6.4, polarity of the carbonyl group. So let's draw that down as well. Let's do it up here. We have an arrow. I guess we should complete the arrow with a little cross at the bottom. And they do it in green. will also make a ketone with the delta minus on top and the delta plus on bottom. All right. Formation. Aldehydes and ketones can be produced by several mechanisms. An aldehyde can be obtained from the partial oxidation of a primary alcohol, although only by pyridinium chlorochromate, PCC, or chrome oxide, what is this? Is this the solution that it needs to be in? Although only by pyridinium chlorochromate, PCC. With any stronger oxidants, aldehydes will continue to be oxidized to carboxylic acids. A ketone can be obtained from the oxidation of a secondary alcohol. This can be performed using reagents ranging from sodium or potassium dichromate salts to chromium trioxide to PCC. When oxidizing a secondary alcohol, there is no concern for oxidizing too far because the reactions will stop at the ketone stage. So we've kind of gone over this before, but primary alcohols get oxidized to aldehydes by PCC, but everything else will oxidize it further to carboxylic acids. And secondary alcohols get oxidized to ketones. Other oxidizing compounds include chromium trioxide, CrO3, so CrO3Cl, where that's the cation, and then dichromate salts, where the oxide, the chromium oxide, is the anion. So we have the cation. We also have the Cr2O7 anion. Like in Na, sodium dichromate salts. All right. What is the suffix for an aldehyde and for a ketone? For an aldehyde, it's Al. For a ketone, it's ONE or ketone, Ketone. Given an alkane, an aldehyde, and an alcohol with equal length carbon chains, which will have the highest boiling point and why? An alkane an aldehyde, and an alcohol. An alcohol will have the highest boiling point, then alkanes, and then aldehydes, because aldehydes do not have the boiling point elevation because they don't make hydrogen bonds. Is the carbon of a carbonyl electrophilic or nucleophilic, and why? It depends. It can be both. The carbonyl carbon makes a good electron withdrawing group, or the oxygen, the double bond, makes a good electron withdrawing, making the carbonyl carbon electrophilic. What is one method for forming an aldehyde and a ketone? Aldehydes can be oxidized from primary alcohols using PCC. Ketones can be oxidized from secondary alcohols using pretty much any oxidant or oxidizing agent. Let's see what they have for answers. 1. The suffix for an aldehyde is al, suffix for a ketone is one. The alkane will have the lowest boiling point. Okay, well there you go. Aldehydes still have a higher boiling point than alkanes, just not as much as the alcohols. So alkane will have the lowest, followed by aldehyde, and then the alcohol. The boiling point of the aldehyde is elevated by its dipole, but the boiling point of an alcohol is further elevated by hydrogen bonds. All right, so it still has dipole-dipole interactions that increase the boiling point for aldehydes. Number 3, the carbon in a carbonyl is electrophilic. It is partially positively charged because oxygen is highly electron withdrawing. Number 4, aldehydes can be formed by the oxidation of primary alcohols, but can only be produced using weaker anhydrous oxidizing agents like PCC. Otherwise, they will oxidize fully to carboxylic acids. Ketones can be formed by the oxidation of secondary alcohols. Other methods can be used as well. Ozonolysis, Friedel-Crafts acylation, but these are outside the scope of the MCAT. Outside the scope of the MCAT, but let's write down anyways. Ozonolysis, Friedel-Crafts acylation, put these in red over here. All right. Nucleophilic addition reactions. Nucleophilic addition. In each of the following reactions, the general reaction mechanism is the same: nucleophilic addition to a carbonyl. This is one of the most important reaction mechanisms on the MCAT, and many of the reactions of aldehydes, ketones, and more complex molecules share this general reaction mechanism. Rather than memorizing each reaction individually, focus on the overall pattern, then learn how a particular reaction exemplifies it. As we have seen, the CO double bond is polarized with a partial positive charge on the carbonyl carbon and a partial negative charge on the oxygen. This makes the carbonyl carbon an electrophile ripe for nucleophilic attack. When the nucleophile attacks, it forms a covalent bond to the carbon, breaking the pi bond in the carbonyl. The electrons from the pi bond are pushed into the oxygen atom. Oxygen happily accepts extra electrons due to its electronegativity. Breaking the pi bond forms a tetrahedral intermediate. Anytime a carbonyl is opened, one should ask, can I reform the carbonyl? If no good leaving group is present, as is the case with aldehydes and ketones, the carbonyl will not reform. Generally, Oxygen will accept a proton from the solvent to form a hydroxyl group, resulting in an alcohol. However, if a good leaving group is present, as is the case with carboxylic acids and their derivatives, the carbonyl double bond can reform, pushing off the leaving group. Figure 6.5 shows the reaction mechanism of nucleophilic addition for an aldehyde. All right, so we have nucleophilic addition. We have a nucleophile attacks the carbonyl carbon, opening the carbonyl. The carbonyl cannot reform because there is no good leaving group. Thus, the O- is protonated to generate an alcohol. So we have the nucleophile attacking, the pi bond breaking. I guess that's what they call opening the carbonyl. Now this oxygen with an extra couple electrons on it grabs a hydrogen to make an alcohol. So let's draw this mechanism in green, the way we're using the same colors that they did. Got the hydrogen, we got an O-. Still got that hydrogen. We have this nucleophile now. And then over here we have an OH. Still got the hydrogen. We have a nucleophile. All right. Over here we have a nucleophile attacking. Here we have an H+. Let's fill it in with some arrows. And some red arrows to signify the attack. All right. That is our nucleophilic addition. Then we have hydration. In the presence of water, aldehydes and ketones react to form geminal diols, as shown in figure 6.6. In this case, the nucleophilic oxygen in water attacks the electrophilic carbonyl carbon. This hydration reaction normally proceeds slowly, but we can increase the rate by adding a small amount of catalytic acid or base. And in 6.6, the carbonyl is hydrated by water, then protonated, resulting in a geminal diol. So let's draw this as well. And then the red arrows to attack, we have the oxygen on the H2O attacking the electrophile. We have the carbonyl opening up. Now we have this negative charge on the oxygen. The oxygen grabs one of this positive oxygen's two hydrogens, and they both become alcohols. So then I guess we'll draw this oxygen attacking a hydrogen, and the electrons from this bond neutralizing Why isn't this working? Is it just out of batteries, probably? Shoot. Heck, it must be out of batteries. Shoot. Well, guess I'm going to have to take a little break. Didn't even get through this hydration reaction. But you see what's supposed to happen here, I imagine. This electrons from this bond go back to neutralize the oxygen. That looks funny. All right. What you're left with is a geminal diol. That's hydration. Next is acetyls and hemiacetals. But I'm sure this... Oh, okay. I guess my Apple Pencil's okay. Just didn't want to connect for a minute. All right, next. Acetyls and hemiacetals. A similar reaction occurs when aldehydes and ketones are treated with alcohols. When one equivalent of alcohol, the nucleophile in this reaction, is added to an aldehyde or ketone, the product is a hemiacetal or hemiketal, respectively, as shown in figure 6.7. Hemiacetals and hemiketals can be recognized by the retention of the hydroxyl group. This halfway step, hence the hemi prefix, is the endpoint in basic conditions. So while hydration can happen in acidic or basic conditions, these acetyls are going to be in basic conditions. You have an aldehyde. The oxygen in the alcohol functions as the nucleophile, attacking the carbonyl carbon and generating a hemiacetal. So let's draw this mechanism as well. Hemisetal formation. Start with our aldehyde being attacked by an ROH. We have the carbonyl opening. Similar to hydration, but instead of an H2O attacking. There's an ROH attacking. And then finally we have the negative oxygen on top attacking the free hydrogen on the oxygen on the bottom. And some red arrows to show the lone pair on the oxygen attacking the carbonyl. Carbonyl opening up, making a negative oxygen, and then that negative oxygen attacking the hydrogen that came in with the alcohol. Aldehyde over here to Hemi Acetyl. And this is in basic conditions using 1 times the OH Now, when 2 equivalents of alcohol are added, the reaction proceeds to completion, resulting in the formation of an acetyl or ketyl, as shown in figure 6.8. This reaction proceeds by a nucleophilic substitution reaction, SN1, and is catalyzed by anhydrous acid. The hydroxyl group of a hemiacetal or hemiketyl is protonated under acidic conditions and lost as a molecule of water. A carbocation is thus formed, and another equivalent of alcohol attacks this carbocation, resulting in the formation of an acetyl or ketyl. Acetyls and ketyls, which are comparatively inert, are frequently used as protecting groups for carbonyl functionalities. Molecules with protecting groups can easily be converted back to carbonyls with aqueous acid and heat. So acidic conditions in both directions, but heat in the reverse direction to get it go back from an acetyl to a hemiacetal, I guess. Or from an acetyl back to a aldehyde. So we have 6.8, acetyls and ketyl formation. We have 1 equivalent of alcohol takes acetyls to hemiacetals. That second equivalent will take it to acetyls. Similarly, 1 equivalent of alcohol will take a ketone to a hemiketyl, and a second equivalent will take it from the hemiketyl to the ketyl. Via second ROH, second equivalent is a substitution reaction. Rather than a carbonyl opening. So let's draw this as well. Let's aldehyde to hemi acetal to the acetal. We have the ketone to the hemiketal to the ketal. So let's also write down that this second step happened via an SN1 reaction, while the first happens via so it's not an SN1, it's just what? Just an addition reaction? SN1 first. Just alkene addition? Nucleophilic addition, right? This one, nucleophilic addition. Oh, this is one of the kinds of nucleophilic addition. It's just that second part is SN1. Should we call this A sub N? This is nucleophilic substitution, SN, so we'll go AN. Sure. All right. Next, imines and enamines. Nitrogen-based functional groups act as good nucleophiles due to the lone pair of electrons on nitrogen and react readily with the electrophilic carbonyl of aldehydes and ketones. In the simplest case, ammonia adds to the carbon atom of water, and water is lost, producing an imine, a compound with a nitrogen atom double bonded to a carbon atom. This reaction is shown in figure 6.9 because a small molecule is lost during the formation of a bond between two molecules. This is an example of a condensation reaction. Because nitrogen replaces the carbonyl oxygen, this is also an example of a nucleophilic substitution. Some common ammonia derivatives that react with aldehyde and ketones are hydroxylamine, hydrazine, and semicarbazide. These form oximes, hydrazones, and semicarbazones, respectively. All right, amines and enamines. So imine just means carbon double bonded to a nitrogen. This is a condensation reaction. Which is also an example of nucleophilic substitution. I need to write all that down. Just go SN reaction. Some common ammonia derivatives that react with aldehydes and ketones are hydroxylamine, hydroxylamine, hydrazine, and semicarbazide, which form oximes, hydrazones, and semicarbazones, respectively. So, hydroxylamine, hydrazine, and semicarbazide make oximes, hydrazones, and semicarbazone. All right, let's take a look at this reaction. Imines and related compounds can undergo tautomerization to form enamines, which contain both a double bond and a nitrogen-containing group. This is analogous to the keto-enol tautomerization of carbonyl compounds and will be explored in Chapter 7. In 6.9, imine formation, ammonia is added to the carbonyl, resulting in the elimination of water and generating an imine. All right, I'm going to draw this out carefully. What we have is the O double bonded to the C and two R groups. We have this NH3 with lone pairs on the nitrogen. Second step, we have negatively charged oxygen, single bonded to the carbon, still bonded to two R groups, and single bonded to this nitrogen that just came in, which is now positively charged. We lose some hydrogen, but we also gain some hydrogen. So you could see this oxygen grabbing another hydrogen, or you could see it as an oxygen taking a hydrogen from the NH3. Either way, in the third step, we have H2O, the oxygen has been hydrated. We have our carbon still attached to its R groups, and we have this nitrogen with two hydrogens on it and an extra lone pair. And that's going to attack a second time and make a double bond. and then water will leave. So finally, all we have left is just the carbon bonded to two R groups, and then the nitrogen is now double bonded. Still has that positive charge. I guess you got to lose the charge by losing a hydrogen to water. So you end up with this molecule right here and water. Let's draw some arrows. And finally, let's draw some red arrows to show the nucleophilic attack. Initial, you have the carbonyl opening. Then we have that negative oxygen attacking a hydrogen. And then we have that nucleophilic nitrogen attacking a second time to make that double bond. And we have the leaving group, water. And that is our imine formation. Next we have cyanohydrins. Cyanohydrins. Hydrogen cyanide, HCN, is a classic nucleophile on the MCAT. HCN has both triple bonds and an electronegative nitrogen atom, rendering it relatively acidic with a pKa of 9.2. After the hydrogen dissociates, the nucleophilic cyanide anion can attack the carbonyl carbon atom, as shown in figure 610. Reactions with aldehydes and ketones produce stable compounds called cyanohydrins once the oxygen has been reprotonated. The cyanohydrin gains its stability from the newly formed CC carbon-carbon bond. So we have a cyanohydrin formation. Cyanide functions as a nucleophile, attacking the carbonyl carbon and generating a cyanohydrin. So let's draw this as well. We have we have hydrogen cyanide dissociating. So we have a Cn- ion attacking our ketone. Next step, we have our negatively charged oxygen attacking a free hydrogen, getting protonated, and your result is a cyanohydrin. Put some arrows in there. And some red arrows to signify the nitrogen attacking the carbonyl opening up, and then the negative oxygen going in attacking a proton. All right. When an aldehyde or ketone is reacted with an equivalent of an alcohol, what occurs? What would be different if it were reacted with two equivalents in acidic conditions? One equivalent would make a hemisetal, while 2 equivalents will make your acetyl. Same thing with the ketone. 1 equivalent would make the hemiketal. 2 equivalents would make the ketal. 2. When nitrogen or nitrogen-containing derivatives react with aldehydes and ketones, what type of reaction happens and what functional group is formed? With aldehydes, you'll have cyanohydrins. The functional group is called cyanohydrins, I guess. When those cyanohydrins is the hydrogen cyanide. When number 3, when hydrogen cyanide reacts with an aldehyde or ketone, it makes a cyanohydrin. The product is stable once the oxygen is reprotonated. For number 2, nitrogen containing is just an imine. Imine is the nitrogen-carbon double bond. And enamines are just imines that undergo tautomerization. So they give us an example of imine. They don't give us the enamine. Enamine is when what is tautomerization again? Let's double check what tautomerization. Tautomerization. Is a net process by which protons are transferred from one site to another by a series of steps in which the solvent is an intermediary. So the keto-enol is keto is the double bond to oxygen. Enol is where the double bond moves and the oxygen gets a hydrogen. So if this were to tautomerize, that would mean that this double bond would move to one of the R groups, and then the nitrogen would get an extra hydrogen on it. So let's make a little diagram of what that might look like. If this was our R group, let's say our R, C, and a double bond to another R, and then this is a single bond to NH2. Let's say it gets an extra hydrogen to deal with that charge. That would be our enamine. But we're going to get more into that in chapter 7, apparently. But I imagine this is what it would look like. So, going back to what they were saying, when nitrogen reacts with aldehydes and ketones, you get imines. And the functional group is the imine, the nitrogen carbon double bond. In number 3, it's cyanohydrin, and this product is stable. Let's double check our answers. (6)2. With one equivalent of alcohol, aldehydes and ketones will form Hemi Acetyls and Hemi Ketones, respectively. With two equivalents of alcohol, the reaction will run to completion, forming acetyls and ketones, respectively. Number 2, the reaction that occurs in a condensation reaction is a condensation reaction because a small molecule is lost, and also a nucleophilic substitution reaction. This reaction results in the formation of an imine, or for nitrogen-containing derivatives, oximes, hydrozones, or semicarbozones. Number 3, when HCN reacts with an aldehyde or ketone, a cyanohydrin is produced, which is a stable product. So 2, I guess I didn't read it carefully. What type of reaction happens is nucleophilic addition followed by substitution, is a condensation reaction, and also a nucleophilic substitution reaction. And this makes an imine. All right. (6.3) Oxidation reduction reactions. Oxidation reduction. Aldehydes occupy the middle of the oxidation reduction spectrum. They are more oxidized than alcohols, but less oxidized than carboxylic acids. Ketones, on the other hand, are as oxidized as secondary carbons can get. Ketones are as oxidized as they can get. Aldehydes can be further oxidized into carboxylic acids. Oxidation of aldehydes. When aldehydes are further oxidized, they form carboxylic acids. Any oxidizing agent stronger than PCC can perform this reaction. Some examples include potassium permanganate, chromium trioxide, silver oxide, and hydrogen peroxide. This is shown in figure 6.11. Most oxidizing agents will turn aldehydes into carboxylic acids. PCC, however, is anhydrous and is not strong enough to oxidize past the point of an aldehyde. In the example, we have an aldehyde going all the way to a carboxylic acid. So we could draw this out since they have it drawn out as well. CH3CH. On the other side we have O bonded to CH3COH. And we're using KMNO4 or CrO3 or Ag2O or H2O2. Pretty simple. Reduction by hydride reagents. Aldehydes and ketones can also undergo reduction to form alcohols. This is often performed with hydride reagents. The most common of these seen on the MCAT are lithium aluminum hydride, LiAlH4, and sodium borohydride, NaBH4. which is often used when milder conditions are needed. This reaction is shown in figure 6.12. AlH4, also sodium borohydride, BH4. And in 6.12, we have ketone reduction using lithium aluminum hydride or sodium borohydride. All right, ketone reduction. Put reduction in parentheses here. All right, what functional group is formed when an aldehyde is oxidized? It is oxidized to a carboxylic acid. What are some common oxidizing agents that assist this reaction? Oxidizing agents would be KMNO4, CrO3, Ag2O, or H2O2. 2. What functional group is formed when aldehydes and ketones are reduced? What are some common reducing agents that assist this reaction? They're reduced to alcohols, and some reducing agents are lithium aluminum hydride and sodium borohydride. Let's check the answers on those. 1. Oxidizing an aldehyde yields a carboxylic acid. Common oxidizing agents, KMNO4, CrO3, Ag2O, and H2O2. Reducing an aldehyde or ketone yields an alcohol. Under certain conditions not tested on the MCAT, aldehydes and ketones can be reduced all the way to alkanes. Common reducing agents include LiAlH4 and NABH4. So they aren't just reduced to alcohols, they can be reduced all the way to alkanes. But that is beyond the scope of the MCAT. All right. Now we got some practice questions. All right. Number 1. All of the following are true with respect to carbonyls except A. The carbonyl carbon is electrophilic. B. The carbonyl oxygen is electron withdrawing. C. A resonance structure of the functional group places a positive charge on the carbonyl carbon. D. The pi electrons are mobile and are pushed toward the carbonyl carbon. So I don't think D is true. I guess C must be true because it's a positive charge on the carbonyl. It's consistent with A and B. So D would be the one that is not true. 2. Order the following compounds by increasing boiling point. Butane, butanol, butanone. Well, butane would be the lowest, butanone would be second, and butanol would be third. So let's go with B. Butane, butanone, butanol. Yeah, B. 3. What is the product of the reaction below? We have a ketone and an alcohol. So I imagine you will get a hemisetal, assuming we have only one equivalent of alcohol, which is what it looks like it probably is going for. So the alcohol will attack the carbonyl carbon, and this oxygen will open up and pick up another hydrogen to balance out its charge. So I think I'm not C2H5 down here. So this second one over here, and this one, it doesn't just pick up a H, it picks up a CH3. I don't think that's right. This is a hemisetal. But it's got a C2H5 on the bottom. This one turned into 2 oxygens. I don't know how that happened. This is basically no reaction. So oxygen plus CH3. No, it's C2H5 is what this is. So this is a C2H5 here on the bottom. So yeah, C looks right. You have C2OH, so C2, but where is the O? Okay, so this C2OH isn't on the right, it's down here on the bottom. This OC2H5 is what is added. All right, that makes a little more sense. It's still C, but I guess it could get a little confusing. What's happening is we have a ketone, we have the alcohol with C2H5 on it. That is this OC2H5. The double bond breaks up and turns into an OH, and then these two constituents, the CH3 and the C2H5, are CH3 and C2O5 here. All right. Just drew it with a little different chirality than we saw in the other example, I guess. What is the product of the reaction below? We have a ketone and nitrogen in ether. So I imagine what we're going for is an imine. I guess what you'll have is the nitrogen attack the carbon. The carbonyl opens up, and then that negatively charged oxygen has to grab something. In this case, it's an ether. So what is ether again? Is ROR. An ester is the carbonyl. The ether is just ROR. So I think what's going to happen is this nitrogen they don't have the oxygen picking up an R in any of these examples. So the ether is not really reacting, it's just this. So you're going to have the nitrogen attacking the oxygen. Attacking the carbonyl, rather. Like in this case. And what happens in our example? In our example, the oxygen leaves with water. So the one without the oxygen is actually the one that looks right. It's like the oxygen is replaced. You have your two R groups. You have a double bond to nitrogen and the rest of this nitrogen compound. We're not going to think about enamines right now, I guess. We're just going to go with an imine. A. 4 is going to be A. 5. What is the product of the reaction below? We have aldehyde and KMNO4, an oxidizing agent. So the ketone will be oxidized into a carboxylic acid. This particular ketone is 1,2 carbon. So it's like a 1, 2, 3 carbons rather. So 2 carbons, C2H5, and then a COOH. C2H5COOH. That looks good to me. Yeah, let's go with 5B. This one has too few carbons. This one's got the right number of carbons, but it's got HO. This one also has the right number of carbons, the wrong number of hydrogens, and oxygens, wrong number of oxygens. So yeah, 5B. On to 6. 6, what is the product of the reaction below? We have a reducing agent, LiAlH4, lithium aluminum hydride. So this ketone will be reduced. Ketones can be reduced to alcohols. So I think this one looks right here, B. Doesn't need to break it up. Doesn't get too alcohols. It only gets one hydroxyl at the end. This is nitrogen. I don't know where that came from. We're looking at B. 6 has got to be B. 7. What is the product of the reaction between benzaldehyde and an excess of ethanol in the presence of anhydrous HCl? In the presence of acid, benzaldehyde and aldehyde with an alcohol. So an aldehyde and an alcohol will make a hemisetal or acetal. Excess of ethanol. I think they tell us excess because it's not just one equivalent of alcohol. It's enough to make a full acetal. So, how do we turn this benzaldehyde, which would be a benzene ring, which would be kind of closest to this, benzaldehyde. Benzene double bonded to an oxygen. Now, I guess it's got to be one away because it's got to have a hydrogen on it too. So it's got to be carbon, oxygen, and a hydrogen here. So that's our benzaldehyde. And we're going to try to oxidize this aldehyde. Whoops. Into our carboxylic acid. So I think what you would end up with looks like this. It's not one of the options. I guess it wouldn't just be an OH though. It would be this R group. It would be a CH3CH2. So I think the CH3CH2, that comes out to C2H5. C2H5O would be but it's not double bonded. I would have thought it would have been double bonded. So what's going to happen here? We have this alcohol, CH3CH2OH. We have this attacking the carbonyl, and then this opening up to make this structure. CH3CH2. And this is going to grab a hydrogen. Or will it grab something else? Oh yeah, this will grab a hydrogen. So let's adjust this just a little bit. This looks like this one over here. So that looks good. I like the way this looks. I think it's got to be C. I don't think you're going to get two alcohols attaching to the same carbonyl. So neither of these are going to be right. And this I just don't like because I don't think you're going to get another benzaldehyde. You're going to get the alcohol is what's going to attack. So I don't think you'll get another benzaldehyde here. I think C is what you're looking for. All right. Number 8, Hemi Acetyls and Hemiacetals usually keep reacting to form acetyls and ketones. Why is it difficult to isolate hemiacetals and hemiketones? These molecules are unstable. The hydroxyl group is rapidly protonated and lost as water under acidic conditions, leaving behind a reactive carbocation, or the molecules are extremely basic and react rapidly with one another. Well, let's look at our hemiacetals. The hydroxyl group is rapidly protonated and lost as water under acidic conditions, leaving behind a reactive carbocation. That sounds right. In an SN1 in a substitution reaction, molecules are basic and react rapidly with one another. I don't think that's the case. I think it's 2 sounds the best. So 1 and 2, 2 and 3, 1, 2 and 3. Are hemiacetals stable? In the formation of hemicetals, hemiketals, alcohol is the nucleophile and the carbonyl carbon is the electrophile. In the formation of acetyls and ketones, alcohol is the nucleophile and the carbocation, formerly the carbonyl carbon, is the electrophile. Right. Let's see. They're electrophiles. Are they basic? Sure. Or no. Nucleophiles are basic. Electrophiles are acidic. It doesn't ever say that they're unstable. Acetyls and ketones, which are comparatively inert, are frequently used as protecting groups. The hydroxyl group of a hemiacetal or hemiketal is protonated under acidic conditions. So I don't think 3 is right. So let's go with 1 and 2. Molecules are unstable, and the hydroxyl group is protonated and lost as water under acidic conditions, leaving behind a reactive carbocation. Let's go with 1 and 2. 8 is going to be B. Nine, in a hemiacetal and central carbon, the central carbon is bonded to. In a hemiacetal, the central carbon is bonded to oxygen, oxygen. OH, OR, H, and R. It's not 2 ORs. OH, OR, R, and R. It's not 2 R's. That would be the ketal. OR, OR, 2 ORs once again is the full acetal or ketal. In this case, it's ketal with 2 R's. This is 1 R, 1 H, and 1 OH and 1 OR. So the first one, 9A, is right. 10. In a reaction between hydrogen cyanide, butyraldehyde, and ethyl methyl ketone, which compound will come together to form the major product? Hydrogen cyanide, an aldehyde, and a ketone. We have butyl aldehyde and ethyl methyl ketone. Well, ketones there's more steric hindrance to ketones. Butyraldehyde, the aldehyde, would react first, I think. So, let's just say hydrogen cyanide and butyraldehyde. Butyraldehyde and hydrogen cyanide, A. Not B, not C. No reaction will occur, also probably not true. Butyraldehyde and hydrogen cyanide, 10A. 11. Which of the following describes pyridinium chlorochromate, PCC, an oxidant that can form aldehydes from primary alcohols, an oxidant that can completely oxidize primary alcohols, an oxidant that can completely oxidize secondary alcohols? So I guess 1 and 3. It doesn't completely oxidize primary alcohols. So yeah, 1 and 3. 11 is C. 12. To form a geminal diol, which of the following could attack a carbonyl carbon? Geminal diol. Geminal diol, hydration. To form a geminal diol, which of the following could attack a carbonyl carbon? Hydrogen peroxide, water, potassium dichromate, or ethanol? I guess it's water, huh? 12, B. 13. In a reaction between ammonia and glutaraldehyde, what is the major product? aldehyde plus ammonia I guess it'd make an imine, not a cyanohydrin, not a semicarbazone, not a hydrazone, an imine, 13A. Thirteen is A. Just to review, what were those other ones? The carbazone. The the oximes, hydrazones, and semicarbazones. What are those? I want to write down what kinds of molecules, what kinds of atoms those are associated with. I guess I'll put them over here on this side because hydroxylamine is H2NOH. Hydrazine is H2NNH2. And semicarbazide is H2NNHCONH2. So lots of nitrogens in all of them. All right. On to number 14. Which of the following can be used to reduce a ketone to a secondary alcohol? Reducing agents include LiAlH4 and NaBH4. The only one in this list that will reduce is the lithium aluminum hydride. 14 is C. 15, imines naturally tautomerize to form enamines. 15 is D, enamines. Let's see how we did. 1 is D, 2 is B, 3 is C, 4 is A, 5 is B, 6 is B, 7 is D, not C. Because an excess of ethanol is present, the product of the reaction between this aldehyde and ethanol will be an acetal. The benzaldehyde will first be converted to a hemiacetal, shown in choice C, but will then proceed to completion as an acetal. Choices A and B are incorrect because they show the presence of 2 benzene rings in the final product. So not the 2 benzene rings, but C, because it's in the presence of ethanol, the other oxygen will also react to make this diol, or what they call an acetal. Not a hemiacetal, but an acetal. So is this what I drew for it? Right. This will further oxidize to make the full acetyl. This does not happen. All right, 7. D, 8 is going to be B, 9 is going to be A, 10 is going to be A, 11 is going to be C, 12 is going to be B, 13 is A, 14 is C, and 15 is D. Well, there you have it. That is Aldehydes and Ketones, Part 1. Next time, Aldehydes and Ketones, Part 2, Enolates. Thanks for watching. I'll see you next time.